logical connectives. So this is conjunction and disjunction. So conjunction is the and, so it's written like this. The operator is the two slashes, a forward slash and a backslash in the sort of simplest notation. So the idea is a proposition A and B claims that both the proposition A and the proposition B are true. So we can write one like this that claims that 3 plus 4 equals 7 and 2 times 2 equals 4. So we can define that, and if we take this proposition here, we can just confirm to ourselves that that's a prop as we expect. Okay, now up here in this thing, we're defining this example, so we have to actually prove that this is the case, and we'll worry about exactly how to do that in the general case as we go along. Let me delete the bits I put in so we can just continue here. So one thing that you might say when you're proving one of these is that really if we can prove both of those things independently, then we have a proof of the whole thing, right? Because that's essentially what the and says. So the split tactic, which is a new one, says if this is a conjunction, is the sort of the specific case we're dealing with here, if it's a conjunction, just split the conjunction into two separate goals. So we get the goal for 3 plus 4 equals 7, and we get the goal for 2 times 2 equals 4, and then we can go about proving those in the normal way. And in this case, it just requires simplification, so reflexivity can do it very easily. So basically, another sort of thing to add to the kit bag of approaches for this sort of thing is if you have a goal which is a conjunction, then you can use split to turn it into two subgoals. So here's a theorem about introduction of and. So if you have two propositions, A and B, then you can make a proposition A and B. If you read this in a slightly different way, these are the propositions here, and these are proofs of those propositions. So just like we would have, say, if this was type, so sometimes we've had things like for all t type, t arrow something. So this is a type, and the second argument here is a value of whatever type t is. And the same thing is going on here because we're taking two propositions, a value of type A and a value of type B, which will be proofs, and we're returning a proof of A and B. So this is one place where you can sort of see that there's an equivalence here between values and proofs and types and propositions. So in this case, we can prove that this is always the case, that we can do this, so we can introduce all those things. And now we've got a goal A and B up here. And we've got our two assumptions, which are a proof of A and a proof of B, called HA and HB in this case. So because this is a conjunction, we can split it. And one goal is to say, well, now we need a proof of A. Well, we already have one of those, which is HA, so we can just apply that. You could also use the assumption tactic there. And similarly, on the other goal, we've got the goal is B, and we've already got a proof of B, which is HB. All right, so that's a very simple theorem. Okay, so if we think about what's happening here, we can see that there's sort of an equivalence going on here between having a proof of A and a proof of B and having a proof of A and B. But it's another way of looking at this is to say that if you get the proof of A and the proof of B separately, it's equivalent to saying, well, I could equally have been given a proof of A and B, which is sort of one thing. It's a bit like tuppling in if I have a value of type A and a value of type B, I can pair them up together in a product or a tuple like this. So it's analogous to that kind of situation. And so if we do this theorem that we had before, we can prove it in a sort of higher level way, if you like, by saying, well, we're going to use the AND intro to do the split essentially. And now we end up with the two sub-goals which correspond to the assumptions of the AND intro. So we can solve those easily as well. Theorem here, which basically says that if the sum of n and m is 0, then n is 0 and m is 0. So we can prove this fairly straightforwardly. So if we have a usual start n and m, and we'll introduce the nm0 part as a named thing. And because we're at the point where we've got a goal that's a conjunction, we'll split that into two goals. Oops, too far. So we'll go back up here. And so in the first case, we know that n and m is 0, and we want to prove that n must be 0, so we can destruct on n. And that one's easy. Now this one is suspicious because we've got Sn equals 0 as the goal, which can never be true. So we can invert this assumption up here because it can never be true either. So that deals with that side, and then in the other side we just do the same thing basically. We're destructing on n because it's the left argument of the plus, right? Because that's the one that's going to be productive, basically. This one sort of seems like this should be fine because we can simplify in HNM0, and then we've got the assumption, or we could apply HNM0 if we want. Just as a side, it turns out that assumption will do some simplification for us as well, so we can just do assumption at that point. And the final one, again, we've got a contradiction in the top level there, so we can get rid of that, and that we're done. Okay, so there's a few more examples there of how to do this sort of thing. The basic principle is pretty much the same. This one shows a slightly different way to approach the AND. So in this case, we've got an AND as one of our assumptions. So we're basically proving the opposite of the one we were proving before, where we're saying if we know that n equals 0 and we know that m equals 0, then it must be the case that n plus m equals 0. So we can do this in a couple of different ways. We can invert the h, but also we can destruct it. So this will give us two assumptions based on the two pieces of the AND, and we've given them useful names. And now we can just rewrite with those to get 0 plus 0 equals 0, which is easy. So that's fine. You can, instead of doing an intros and then a destruct, this one shows you that you can do the destruct as part of the intros by giving a set of subpatterns here. So that's a little bit shorter. Problem with that is that you have to know that that's going to happen, so it's often not obvious to start with, so you often end up with the destruct first. Okay, so so this is making the point that if you could have an equivalent sort of theorem where the two assumptions that n and m are 0 are separate arguments to the theorem instead of packed together in the AND, and the proof is slightly simpler because you don't have to destruct the AND to get to that point. But sometimes you sort of introduce the ends sort of along the way. So for example, here we're saying, well, if we know that n plus m is 0, then we can show that n times m is 0 as well. And we're going to use the previous theorem that said that we could show that n and n is 0. So we can assert that and then use our previous exercise to just get that. And now we're in this, position where we have the conjunction of n and m being 0. So we can destruct that. And then if we, it doesn't really matter whether we use n is 0 or m is 0 here, because either will lead us to the thing. So we can rewrite, it's probably better to use the one on the left, because then the multiply can be simplified straight to 0. Okay. So this is sort of a general, you may remember this sort of thing from logic courses and things, if you've done that sort of thing. So this is basically saying if I've got two propositions P and Q, and I know that P and Q holds, then I know that P holds. Right? It's a fairly obvious sort of thing, and we can prove it pretty easily by just pulling apart the end. And now we've got a proof of P called HP and a proof of Q called HQ. So we can just apply the P1, okay? And hopefully you can see how to prove this second one very easily as well. And the sorts of properties that logic courses would teach you about conjunction, you can prove those as well. So in this case, this is saying, well, it doesn't really matter which way around you do the end, they're equivalent. So this is only one direction, but it's symmetric. So we can do this, bring that in there. So now we've got an end as our goal. So the standard technique is to split it. And now when we've split, now we need a proof of Q, which we have. And now we need a proof of P, which we have. All right, so that's pretty straightforward. And if we go to the homework, and the SOC is one of the homeworks for this week. Okay, and we haven't sort of seen definitions and things here, but basically the AND notation that we've been using is just syntactic sugar for the AND constructor in this case. So you can see that the type of AND is something that takes two props and builds a prop. So that's what we would expect. Okay, so the story for disjunction is quite similar. The idea is that we need some way of representing, we've got two props and we know that at least one of them is true, then we know that the disjunction, the OR, is true. So analogy to the AND, you use the backslash and then the forward slash to make it look like an OR symbol in mathematics. And we can prove things like this where we know that n is 0 or m is 0. The theorem above was we knew both of them were 0, but here we really only need to know that one of them is 0 to know that the product is 0. Okay. The slight complication here is, let me just sort of show you what this looks like simplified. All right, so if I introduce H, then I can destruct H as like that. And the reason there's a vertical bar in there is because the two constructors here for going on the left and on the right are different things. So I have to give one name for each one of those, as opposed to the AND, which had one constructor that had two arguments. And of course, the simplest version is just to destruct the whole thing in one go. Okay, so in this case, we know that n is 0, so if we rewrite and simplify, we're done. And here, if we rewrite, we can't just simplify here because we've got n times 0, we don't know what n is. So we have a theorem before this mult in 0 which basically just says n times 0 equals 0, so we can rewrite with that there. Okay, it should be possible. Let me just see. It should be possible at this point to just apply not in 0. Oh, because I haven't imported it. That's interesting. Oh no, it's not 0, it's O. Okay, so it's getting a bit confused because it's around the wrong way. So it's the symmetry question. So you see over here it's saying that 0 equals something that's multiplied by 0, and the thing that we're trying to match it with is n times 0 x 0. So this is the arguments around the other way. So the rewrite is simpler in this case, I guess. Okay, so just like we did for the AND, we can think about the introduction sorts of things for OR, just like we did AND intro. So AND intro just said we get, if you have a proof of A and a proof of B, then I can give you a proof of A and B. This one says that if I have a proof of A, I can give you a proof of A or B by using the A part, and we don't care about proofs of B. So we can just introduce that. Now, at this point, we have an OR as the goal. So the in the AND case, we would split at this point, right? But we can't split at this point because we don't have an AND. But we can say that we're going to go about proving this by focusing on the left side of the disjunction, or the right side if that was better. So looking at this, the assumptions here, we've already got a proof of A. So the best way to go is to the left here. If we went to the right, we would need a proof of B, but we don't have one of those. So here we can go to left, and notice that so go backwards and forwards here, the A or B just turns into A, and now we can apply the proof of A that we already have. Okay, so just like with AND, you almost always want to split the goal to deal with the pieces separately. With OR, you generally have to pick one direction, go to the left, go to the right, and hopefully that leads you to a proof of the thing you're interested in. So this example here is saying any number in n is either 0 or the successor of the predecessor of n. In other words, the number before n. And pred in this case is well defined because we're dealing with the cases that aren't 0. So if we do the introduction here, we got these, right? So what this is doing, because of the square brackets, that's doing intros of n and a destruct all in one go. So we end up with two goals, and the first one is the 0 case, so n is 0. So we have to prove that 0 equals 0 or 0 equals s of 0, of the predecessor of 0. And if you think about it, well, obviously the left-hand side is easy to prove. The right-hand side actually isn't possible to prove because it's saying that 0 equals the successor of something, which isn't true. So here we want to go to the left, and then we can easily prove that. In the non-zero case, so this is where we've got s of n, we're not going to be able to prove the left-hand side here, the s of n equals 0, right? Because that can never be true. So we have to go right if we're going to get anywhere. And if we think about what's happening here, we're taking the predecessor of s of n, which is just n. So we've got s of n equals s of n. So I can do the simplification there, and just to make it a bit more obvious what's happening. Okay, so you can prove these other ones. I forget what the homework is now. So these are just for future work if you feel like trying some things. So you can prove the usual things like commutativity of OR and so on and so forth in the same sort of way as the ANDs. Okay, so I'll stop there and pick up with falsehood and so on in the next video.